We can start now.
Hello, everyone. It's a pleasure to introduce today Professor Chris Consolis from the University of Manchester in the United Kingdom. Chris obtained his PhD at the University of Wisconsin-Madison. He has held positions at the Space Telescope Science Institute, at Caltech, and at the University of Nottingham. Since 2010, Chris has been a scientific editor for the Astrophysical Journal, and since 2018, the lead editor for the Galaxies and Cosmologies corridor of the AAS journals. Chris's interests revolve around galaxy formation and evolution, but today he's going to be talking to us about a different topic on intelligent life in the galaxy. Thank you so much, Chris, for accepting our invitation. You may start when you're ready.
Thank you very much for the invitation. I'm happy to be giving this presentation. Wish it was in person, and hopefully someday soon I can come visit again. I was there 3 years ago. Some of you may remember when I was there, and I really had a good time. So hopefully I can come back in person again. So what I want to do today is a little bit different from what I normally work on, which is galaxy formation and the galaxy evolution through time. And what it is essentially looking at the idea that there could be intelligent life within our galaxy and looking at it from a scientific perspective and trying to answer that question, which is how many of these extraterrestrial civilizations might there be throughout our galaxy? So that's, of course, a very important question, and one that we've wondered about now for thousands of years as humans. And it's something that we still don't have an answer to. We don't even have an answer yet about even if life exists outside of the Earth, let alone trying to understand if intelligent life exists, which is, of course, a step up from just having basic life. So as I'm sure all of you have heard about the Venus results of finding some evidence of life that may exist in the atmosphere of Venus, but that would be simple life. And so this is a very interesting topic, of course, and it always will be interesting. And so we always want to try to approach this problem in as many ways as we can. So what I want to do today is really talk about trying to quantify how many of these communicating extraterrestrial intelligent life there might be within our galaxy, besides our own, obviously. And the title is the Astrobiological Copernican Principle. And so what does that mean? So that's sort of a kind of a mouthful of words. And basically what it means is that what we've done in this paper, which I'll come to next, if I can figure out how to advance this paper here, which is essentially all I'm going to talk about today, which was led by a master's student of mine named Tom Westby, who is normally a mathematician, but wanted to do a master's and now perhaps a PhD in astronomy. And this was a topic that I always wanted to write up with some of my ideas, and he was keen to do it. And so this is the result of that. But in any case, what is the Astrobiological Copernican Principle? And there's a weak and a strong limit there. What does that mean? Well, when Copernicus first came up with his idea for the solar system being centered around the sun rather than the Earth, he essentially made one of the first big jumps in our understanding of humans and their place within the universe. So for thousands of years, we thought that the Earth was the center of the entire universe, not just the solar system, but the entire universe. Today, of course, we know that's absolutely not true, but up until the 15th century and even beyond that, for many people, the Earth was the center of everything. And that fit in with religious ideas about humankind being the center of the universe, that the universe was created for humans, and so on and so forth. But Copernicus was the first to show that this was not the case. And then later on, we learned that the sun is not the center of the universe. The sun is not even the center of our galaxy. Our galaxy is not the center of the universe. The cluster we're in, if you want to look at it even further, or the group that we're in, is not the center of the universe, and so on and so forth. And so it's obvious to us now that in no way are we special within the universe. Within an astronomical context, humans are not special in any way. So this goes a step beyond all of that and says, well, if this is all true, then why not our own existence as an intelligent species? Why are we special? And the idea here is that if you have the right conditions to form life, to form intelligent life, and we use the Earth as a basis for the conditions that you need, then you will naturally form life. That is, that our existence, our biogenesis is not special, but is something that came about through science. And so if you have the same conditions in the same amount of time, which is about 5 billion years to form intelligent life within the Earth, then it will naturally happen. So that's the basic idea. And we'll come back to the weak and strong limits and what they mean in a little bit. So here's the paper, and I'm not going to read the abstract and bore you, but it's on the archive. It's on, it's in the journal. So if you're interested in the details of anything I talk about, please go to this paper. Okay, so as I've already said, this question is, of course, a very popular one and one that's been around for a very long time. Are we alone, right? And so the first person to make an attempt to calculate how many of these civilizations there might be within our galaxy was Frank Drake. He came up with the now famous Trig Equation in 1961. And this equation basically came up with a bunch of terms which were used to calculate how many intelligent communicating civilizations that there might be within our own galaxy. And I won't spend too much time on this, but it's important that we understand what the Trig Equation actually says. And there's many ways of talking about this equation. So this is the equation itself. So N is the number of intelligent communicating civilizations within the galaxy. Then you have this quantity called R star. This is the average star formation rate of the galaxy. Now, what does that mean? That just means what is the average amount of stellar mass formed within the galaxy over time. So you could think of it as just the total amount of mass that's formed in stars in our galaxy today divided by the lifetime of the galaxy. Okay, and that would give you an average star formation rate. That is how many stars, how much mass is formed in stars per unit time. Okay, F of P is the fraction of stars with planets, and I should say that none of these quantities were known in 1961. In fact, the one that we learned about earliest was R star. That is something that we had some idea of maybe in the 1990s. But before that, we knew nothing about any of these quantities. But F of P and R star, we know basically what those values are today. And I'll come back to that later. So F of P is just the fraction of these stars with planets, fraction of stars with planets. N of E is the average number of those planets that could host life, okay? Then you have F of L, which is those planets that actually develop life. And then you have F of I, which is the fraction of those which develop intelligent life. And then you have F of C, which is the fraction of those that release signals that could be detected. And then you have L, which is the average lifetime of a communicating civilization. That is, how long did these civilizations actually transmit signals that could be detected? Now, the problem with the Drake equation is that although we do know some of these terms, like R star and F of P, and in principle, we might be able to learn L from our own lifetime of our own civilization, we have no way of knowing what these other terms are until we detect life itself. So you can't solve this equation for N until you actually have measured N. That is, you won't ever know what F of L, F of I, F of C, especially those terms are until you actually know what N is and you can solve for those terms. There's no other way of knowing this. You can maybe come up with guesses, and this is what people have been doing for decades. And you can maybe, if you're clever enough, come up with a theoretical reason for these values. But empirically, observationally, you'll never know what the value of N is from this equation until you actually measure N. So in some sense, it's not a very useful equation. So what we did was come up with this idea, which I've already introduced, so I won't go into it again, is the Astrobiological Copernican principle, which is essentially that if you have enough time on a planet, which is in a star, which is stable, over 5 billion years, then you will form intelligent communicating life, just like we have in our own case. So again, this comes back to this philosophical idea that we are not unique, and that if you have the right conditions somewhere else in the universe, you will also form intelligent life. That's the idea. Okay, so let's not berate the point anymore, and let's move on. So based on that assumption, you can, if you want to think of it as a rewrite of the Drake equation, you can, but we call it the CETI equation. And it's a little bit different than Drake because it has terms that you can actually measure, except for one of them, which I'll come back to later. One of them is one that we have to basically infer. And I'll, again, talk about how we do that based on the Earth. So the CETI equation is that the number of civilizations within our galaxy is equal to n star, which is the total number of stars within our galaxy. Okay, that's easy. That's how many stars you have in the galaxy. F of L is the fraction of those stars which are older than 5 gigayears. Okay, so that's again going back to this Copernican astrobiological idea. You need 5 billion years to form intelligent life within our own planet. So therefore, we're making the assumption that that is about the amount of time you need. Now we have an error range in that. It's not exactly 5 because that would be very strange, but around 5. Then FHZ is a fraction of those stars which host a suitable planet in a habitable zone which could support life. So this is something which we also recently learned from the Kepler satellite, which is how many planets, or the fraction how many stars and the fraction of those stars which have a planet in the habitable zone. And the habitable zone is, for those who aren't familiar with it, is the zone around a star where the temperature is not so hot nor too cold such that life can exist. If you have something which is too hot, like on, well, I should say Venus, but we don't know that now. On Venus or Mercury, it's too hot to form life. And if it's too cold, like at Pluto or somewhere like that, or even Jupiter, then it's too cold, right? So you need a nice temperature like we have on Earth with some range to form life. Okay, and then F of M is a fraction of stars which host a metal-rich planet. Okay, so this is based on metallicity of stars, because we know that stars and the planets they host have a metallicity which correlates. So if you have a metal-rich star, you get metal-rich planets and so on. Metal poor, metal poor. So F of M is just saying, well, you need a metal-rich system to form intelligent communicating life, right? If we didn't have metals, we didn't have, metals and iron and stuff, we couldn't have technology, we couldn't have our computers, we couldn't have, satellite dishes and so on, right? You can't make intelligent communicating life out of hydrogen and helium, out of the Big Bang elements, or even just basic elements. You need pretty metal-rich elements to form a technology. Okay, I think that's not a too difficult point to agree on. So that is one thing we also examine. And then we have this fraction L over tau, and L is the average lifetime of an advanced civilization, or basically how long a civilization on average will be transmitting some kind of signals that can be detected into space. And we'll come back to that again. And then tau prime is the average amount of time that a star is old enough to have hosted intelligent communicating life. Okay, and that comes back to this astrobiological Copernican principle, where you have certain conditions in the weak and strong depending on how long you think, or when the sort of the window is to form intelligent communicating life. So on Earth, we know it happened after about 4.5 billion years, and that's the basic assumption we make, but you could imagine a case where it could happen in 4.5 billion years, or 5.5 billion, or 5 billion. So there's some range there, and that's tau. Tau is that range. And you can also have a condition, and that's a strong criteria. And the weak criteria is where you need to form life after that limit, but it can happen at any time. So after 5 billion years, if your star is 10 billion years old, then intelligent life could form anytime after 5 up to the age of the star. So that's 5. In the case of a star which is 10 billion years old, you have 5 billion years to form life. So that's the weak principle. So strong means it's around 5 billion years, and weak means you need at least 5 billion years. It could be longer, but it can't be shorter. But actually, it turns out that if you use 4 billion years or 3 billion years, it doesn't make much difference, as we'll come to. Okay, so let's start looking at these terms. So the first one is the ages. We need to know the ages of stars and the star formation history, and we need to know those things. And this is where my galaxy background comes into use here. We need to know essentially how many stars are older than 5 billion years, and we need to know what is the average age of stars to actually calculate this tau value of how long a star could have hosted intelligent life, or how long it could have developed. So when you look at this, and this is the star formation history of the entire universe, which is what we use as a proxy for the star formation history of our own galaxy. And that assumption is necessary because we actually don't know the star formation history of our own galaxy very well. It's very hard to know what it is based on looking at stars, which is amazing to me. But this is what I learned looking into this problem, is that we don't actually know the star formation history of our own galaxy. But if we look at other galaxies nearby, or even in our local group, it pretty much matches quite well the star formation history of the global universe. Anyway, it's going to be approximately right, let's say. But what you find when you do this, it doesn't make much difference. You find that F of L, which is a reminder, is the fraction of stars older than 5 billion years, is about 96%, which is a large fraction. That's almost 100% of the stars within our own galaxy, which are old enough to host intelligent life in our galaxy. Sorry, my daughter just walked in. Okay.
Look. I love that very, very much, she says.
Okay, thank you. Sorry about that.
No worries, no worries.
I knew that was going to happen. This is what happens when you I give a talk at 7 o'clock at night. So the fraction of stars which are older than 5 billion years is about 96%, 97%. And that's a high fraction. So it's almost 100%. It doesn't really make a difference. And even if you use 100%, it doesn't matter. So this is somewhat surprising to me when I did this, because I thought, well, 96% of stars in our galaxy are older than 5 billion years. You know, that's a huge fraction of the stars, because, you know, we think of stars as, you know, star formation is happening still and so on. And 5 billion years is not you know, even half the age of the galaxy, but it is a significant fraction of the life. And the reason for this fraction being so high is because the number of stars in our galaxy are dominated by M dwarfs. They're dominated by very low mass stars. And those dominate the stellar mass function. And so when you have star formation happening in the very early part of the galaxy and up to the peak, which is about 8 billion years ago, the vast majority of those stars formed are going to be M dwarfs. And that's true of even star formation today, is that most stars are very low mass stars. And so most of these stars are quite low mass. If you wanted to look at this fraction for like G stars, like the sun, it would be much lower. All right, the other thing you can do with this, which is more useful, is that the mean age of stars in our own galaxy after 5 billion years is about 4.8. So the mean age of stars is about 9.8 billion years. So 9.8 billion years is the average age for stars within our galaxy. And that is something that you need to know the star formation history to actually compute. Okay, so we can measure that from this. And there's all kind of integrals and stuff we did in initial mass functions, which I won't have time to go into. But if you're interested in that, it's all in the paper. Okay, so one of the things that we also want to know is where are stars distributed within our galaxy. And this is important for understanding things like how far away stars are in terms of trying to communicate with any kind of CETI that is trying to find and locate these things. Where might they exist? And so what we've done is divide the galaxy into different regions here. And you can see that we've labeled them with letters, A, B, C, D, E, F, G, etc. And D is essentially where the sun is found. And A is the center of the galaxy. Okay. And then we have above the plane, we have letters going up to Z, and then even up here to and pound sign, because we ran out of letters to use. So this is essentially the way we map the galaxy itself. Okay. And if you look at things like the distribution of stars, this is what you find in terms of where they're located. So this is looking at things in terms of different areas of the galaxy with these letters that I explained earlier. So here you have 35% in A. So that's 35% of all the stars are within this region A, the center, and then near us, you have 6% of the stars. And then obviously, as you go further outside the plane here and further away from the center, you get less and less fraction of stars, such that in the outer parts here, you get a very low fraction of about 0.04%. So that's essentially how this distribution is done. And this is again done so that we can say where are these CETI likely to exist? How far away are they, etc. And then also it gives us an idea of the total number of stars in the Milky Way galaxy, which is about 2.5 times 10 to the 11. So that's about 250 billion stars within our own galaxy. Okay. So that's the information on the number of stars and where they are. And this just shows what I've already talked about, which is the age distribution of stars in the Milky Way. And so here you have a plot showing the fraction of stars younger than a given age. So if you look, and that's the blue line there, if you look at 13.7, which is the age of the universe, you find that 100% of all the stars are younger than that. Obviously, they have to be. Then as you go further to lower ages, the curve changes. The sun is that purple dashed line. So that's 5 gigayears. So the sun is a very late term star in terms of its formation in the galaxy. And you can see here that almost all the stars in our galaxy are older than the sun. So our sun is formed and our existence happens quite late in the history of the galaxy. It's something that, we all know that, right? We all, 5 billion years for the sun, in the galaxy is 13.7. But if you look at it like this, it really shows you how young we are in our galaxy compared to other stars. I mean, there's hardly anything which is as young as us. So relatively speaking, the sun is very young, and we're definitely a latecomer to the galaxy. So the median age is shown there as the dashed green line, and that is, again, 9.8 gigayears. So 4.8 gigayears after 5 gigayears for the time you would have to form life within the galaxy. And the median age is 10.35 billion years. So it's a little bit different due to the fact that most of those stars are very low mass. Okay, so that's how we get those values there. Okay, so the habitable zone, we talked about this already, and I'm not going to go into it in more detail, but you can think of it as this blue strip here, where the sun is here on the left, and the planets are here, including Pluto. And so if you're a fan of Pluto, you should be happy with that. And this blue region shows the habitable zone for stars of different masses. So the sun is here in the middle, and the Earth is here right in the middle of the habitable zone. And some people think that Mars is also in the habitable zone. So this would be a little bit larger if you're one of those people. And even some people think Venus might be in the habitable zone as well. Although I wouldn't agree with that, but some people do. And if you have a cooler star, like in the bottom, the habitable zone is closer to the star. And if you have a brighter or luminous star, the habitable zone is further out. Okay, so that's the idea. So it's pretty straightforward. And we have found lots of planets in the habitable zone. So this is one of the big successes in all of astronomy, I would say, in the last 10 years, that we know that planets exist in the habitable zone of stars, and they're actually quite common. So here's an example of the TRAPPIST-1 system, which found several planets in its own habitable zone and several other planets which aren't. So it looks sort of like our own solar system. And what has been done is to calculate actually the fraction of stars which have a planet in the habitable zone as a function of spectral type. And this is a table I took right from our paper. So here's FGK stars, and here's M stars below it. And this is the reference. And you can see that the fraction of stars for FGK stars is about 15%. And for M stars, it's about, the fraction of those stars is, sorry, no, it's right here. It's the wrong column, sorry. It's about 34%, and then the fraction of M-type stars is 16%. And if you do a weighted mean of these things, you find that the average is about 0.19 for all stars. And this is because most stars are M stars, so the average will be more in line with 0.16 than, say, 0.34. So we not only know that stars are in the habitable zone, but we also know the fraction of stars as a function of spectral type, which are within that zone. So therefore, we can go back. And so let's just review here. We can go back to our friendly CETI equation. So in star, we know F of L, fraction of stars that are older than 5 gigayears, we know. Then F of HZ, fraction of stars which have a planet in the habitable zone, is also known. So now we have to figure out F of M, metallicity, and this term L And tau we also already know because we can measure the ages of stars within our galaxy. So let's go to talking about the metallicity. So this is also something that we recently learned from observations, is the metallicity distribution of stars within our galaxy. And so this is a plot of the fraction of stars which are have a metallicity which is at least solar, which is at least the same metallicity as our own galaxy. Sorry, as our own sun, as our own star. And this is the distance from the galactic center. And so this is the fraction. So you find here the red line is basically at the within the plane of the galaxy. You can see here that the fraction is very high. It's almost 80% here, and then drops down quite rapidly. And then as you go further away, the red and the green, further away from the plane, you find that the fraction of stars with this high metallicity is much less. But in any case, this is just a representation of our ability to actually measure metallicities of stars and know where they are in our galaxy. So we can combine this information with the distribution of stars, because we know where stars are and we know the metallicities are, and we can calculate what this F of M term is. And now there's three possibilities that we picked. One is solar, and that is about 50%. So half the stars in our galaxy have a solar metallicity or greater, and then 0.5 and then 0.1. Okay, and so 0.5, you get about 82%, or at least half solar. And then for 0.1 solar, you find that it's about 97%. Okay, so that's pretty high. So if 0.1, you're getting most of the stars in our galaxy. Okay, so let's talk about timescales a little bit, just to put everyone on the same page. So you're all astronomers and not biologists. And let's just review how life occurred on the Earth. So first life occurred about 14 billion years ago, and I'll come back to this again. And that's basically looking at like microbial life, very simple life, which single cell life, that kind of thing. And that happened about 14 billion years ago. And intelligent life, with our very happy caveman here, happened about 6 million years ago, so quite a long time ago. And then recently, we've had communicating intelligent life. Put a question mark there because you can debate how intelligent we really are with everyone on their mobile. And that is, of course, relatively recent. And let's just call that today. So the question is, how long will our civilization last? And this is the big question, of course, almost as big as the one about whether or not there are other communicating extraterrestrial intelligences in our own galaxy. But our technical civilization on Earth is about 100 years old. So I'm often asked, what do I mean by technical civilization, right? So, you could define a technical civilization as something which uses like, I don't know, basic tools, flint tools or something, because that's sort of a technology. For a caveman, that would be technology. Or, if you build like a house or something, that's sort of technology, right? So, but what I mean by technology is something which is transmitting electromagnetic radiation into space, which can be detected in principle by another intelligence that's somewhere else. Okay, so for example, no matter how many flint tools you have, no matter how many horse and carriages and whatever houses you build, you won't be detectable from other planets ever. No matter how much of this technology you build, you need technology which transmits signals into space to be detected. This is almost by definition, okay? And that signal can be, radio waves from satellites, from television, radio, from radar at airports, from even city lights. You could say is one possibility for how we could be detected. And the point is that on Earth itself, we've been around for about 100 years doing this, okay, with various degrees of intensity. Obviously, if you look now, you'd be much easier to find something happening than you would be, in 1850. But about 100 years is how long we've been having a civilization which is transmitting signals into space. Now the question is, how long will we actually be around? And there's many things which can destroy us, and we don't know how long past 100 years we'll be around. So in our paper, we took as a reasonable guess about 100 years, because that's how long we know we've been around. We don't know how much longer we will be around, because there's many things which can destroy us. So let's just say, as a good guess, that 100 years is about how long a typical average communicating civilization will be around. And the problem with a technological civilization is that you not only build cool things like, mobile phones and satellite television and Netflix or whatever, but you also build things like things which pollute, things which cause nuclear war, and random things which split the earth in half, and also, of course, elect people in powerful positions which probably shouldn't be there. Okay. Enough politics. So what do we get? So if we use 100 years as our limit, we can actually start looking at things. And if you want to do a longer time, you can, and the equations work that way. But as a basic idea, for the technology at least, we're looking at things which last for only 100 years. But we can easily look at how things change as a function of that. So there's a couple of categories here, and let me explain them. So ultra weak is just primitive life, and I'll come back to that again. So that's just microbial life, very basic life. And on Earth, only took about 1 billion years for that to form, as far as we know. Then there is the Copernican astrobiological principle criteria, which are weak, moderate, and strong. Now, I already talked about this. So the strong criteria is when you have intelligent communicating life forming at about 5 billion years, but we give a range of 1 billion years for that to happen. Okay, so we're trying to match exactly what happened on Earth, which was about 5 billion years. But of course, it would make no sense. It'd be absurd to think that it happens at exactly 5 billion years that we get communicating intelligent life. And once you start that clock, so to speak, of intelligent communicating life, you only have a certain amount of time before, in principle, it will destroy itself. Okay, so you can have nothing for 9 billion years, and then you form intelligent communicating life. The clock has started, and however long it's going to last, but it starts at that point. Okay, so we give that range of about 1 billion years for that clock to start in terms of when communicating intelligent life begins in the strong principle. Then we have the moderate principle, where you make that time a little bit longer. So anytime between 4 and 6 billion years. And then the full-on weak Copernican principle is that it can happen anytime after 5. Okay, so we formed at about 5, but maybe we could have formed it 6, 7, 8 billion years from now, or from when the sun was formed, right? So that would be billions of years from now. And because there's no reason that you have to have exactly 5, as I said. So it could happen anytime after 5. But that's a weak principle because it differs from what actually happened on Earth, which was about 5. Okay, and so if you want to have a strong criteria, then it matches exactly what happened with us. All right. So that's how that is. That's how that works. It's not complicated. Hopefully I've explained that well enough that you can sort of understand what those mean. And then we looked at the 3 metallicities. And then we were able to calculate based on this, how long how many of these civilizations there might be within our galaxy. And here are the numbers. And so let me move up this thing because Zoom is all blocking my view. 1 second. Okay. So this is the minimum number in the galaxy. And again, this is based on the lifetime of 100 years for an average civilization. And so you can see here, I'm not going to go through all the numbers. The minimum number in the galaxy goes down to 36 on the left. That's the famous number now, which has been reported in the media a number of times without any error bar, but the error bar is there and it goes from about 4 to about 200. So that's the number of civilizations you would expect in our galaxy if the average lifetime of a civilization is 100 years, which matches how long we've been around, and the conditions for formation are exactly the same as ours. So it's really not that many. And then if you look at the minimum distance, you find that it's about 17,000 light years away. Okay, and that's really important, and that's really far away. So 17,000 light years is extremely distant, and it has implications for how you might be able to communicate with any kind of civilization if it's so far away, which I'll come back to in a few slides. Okay, so primitive life is one of the conditions in that table. And that is, again, just, you know, beginning of life happening, microbial life happening in water or whatever. And that is actually quite common, okay? And essentially most planets would form, that's in a habitable zone, would form this kind of life. If you look at our principle that you just need the right conditions, then you would find that there is around 1.6 times 10 to the 11 habitats on our galaxy which could form this kind of life. And that's about almost half, a little bit over half of all stars. And this would be very simple life, such as what we might have found in Venus a few weeks ago, or was it last week? I can't remember, recently. And if we just move on here to the weak category, again, you find that the most optimistic estimate is about 2,900 civilizations within our galaxy. Okay, so that'd be 11 out of every billion stars host one of these civilizations. And the distances would be about 1,800 light years, which is still quite far. So even in these very, say, more optimistic scenarios, life in our galaxy would not be extremely common, unless this lifespan of these civilizations is much longer than 100 years. But if it's 200 years, then you would just double these numbers. And if it was, you know, 1,000 years, then you would multiply it by a factor of 10. Okay, so it depends on how long you think civilization might last on average for these CETIs. Okay, and then the moderate, again, is somewhere in between, and I won't spend much time on this slide, but just to say that it's between that and what we get for the strong, where this is where you get, depending on your criteria, so the most optimistic, you get about 280 civilizations, which would be about 1 out of every billion stars. So you'd have to survey about 1 billion stars to find one active civilization, which is ongoing. And the most conservative, which is 36, you would have at least 4, and that would be about 0.016 out of every billion stars. So that would be extremely difficult to find. Okay, now, can we communicate with these CETIs? And this is an important question because, you know, people want to find aliens, but they also want to talk to aliens for some reason. I personally wouldn't, but a lot of people do. And a lot of people email me saying that they actually have. So I don't think they have, but it seems like a popular thing to want to think about doing. So could we do it? So the answer is it's going to be very hard. And this plot shows how. So each one of these curves here, colored green, yellow, and red. Sorry if you're colorblind, this is not the best plot I meant. But in any case, each line is a different criteria that I just talked about, where the most optimistic one is at the top here. That is, life is very common. That's like the weakest criteria. And then the strongest is at the very bottom. Okay. Now, if your average lifetime of your civilization is short, and this is the axis here on the x-axis, then what you find is that the average distance between the civilizations goes up, okay? And that's just because they're rare, right? So if your average lifetime of your civilizations is small, then there's going to be less of them because they just would have destroyed themselves or have been destroyed by, you know, maybe something astronomical like a supernova or asteroids or something. And if your average lifetime is long, say into the thousands of years, then the distance drops very rapidly, depending on your criteria, okay? So, all right, so actually, no, I made an error here. So this actually is the most optimistic, and this is the most pessimistic up here. Okay, so it's the opposite thing. So the top is the most pessimistic. So in any case, what you find is that these two are correlated. And if you're in the criteria or in the point on this plot, which is to the left, then you would not ever be able to communicate with CETI in any way whatsoever. And the reason is because if you have, let's take an example up here, where you have a short lifetime of your civilization, that means the average distance is, let's say for this line here, let's say a couple hundred years is a lifetime. So in that case, your average distance is about 8,000 light years. So what would happen if you detected something from 8,000 light years away, imagine we did, and the lifetime of that civilization is a few hundred years, then by the time we got that signal, that civilization would have been long extinct, right? over 7,000 years ago, it would have been gone if his lifetime was only a few hundred years. And certainly by the time we send an answer or a signal back saying, hello, we can hear you, that would take another 8,000 years. And they would then, of course, obviously be gone even more. And then we have to wait another 8,000 years to get an answer, right? So you have to be on the right here to actually have any kind of possibility of there being any kind of communication. Now, detection and communication, of course, are different things. But the point of this plot is to show that actually it's very pessimistic to not only have intelligent life within our galaxy, but to try to communicate with it would be really difficult unless the lifespan of average civilizations is very long. And there's reasons to think, based on the Fermi paradox, which I'm happy to go into if people ask me about it, which suggests that this lifetime of civilizations really cannot be very long at all. So sorry to break the bad news, but it doesn't look good for an average lifetime of a intelligent communicating civilization. Okay, so there's a lot more to talk about and all this stuff, but this is a quick summary of the paper and how it and how we're able to calculate these quantities. So just as a quick summary of what I talked about, we can now calculate how many active civilizations there might be in our galaxy based on new astrophysical information, based on the number of stars, based on the lifetime of those stars, based on the fraction which have a planet in the habitable zone. And the range which you might have in our galaxy can be quite large depending on which assumptions you want to believe, but the minimal number is around 4. That's consistent with almost being just 1, if you want, ourselves. If the lifetime is about 100 years, which is the lifetime of our own civilization. Okay, and the key part of this is again the lifetime of civilizations, the average lifetime of civilizations within our galaxy, right? Not just because each one will be a little bit different. So the average is the important thing. And the interesting thing about that is if we are a typical type of communicating intelligent species within our galaxy, then by searching for extraterrestrial life throughout our galaxy, we are actually putting limits on how long we might be around, because the longer that we find no evidence for any kind of CETI throughout our galaxy, the worse it looks for our own long-term survival, simply because if the existence of a communicating intelligence was long, that is, say, millions of years, which would not be out of the question because the galaxy has been around for so long. Millions of years is nothing compared to 13.7 billion years. Then we would find them quite commonly. They should be scattered throughout our galaxy, and we probably should have detected something by now. Okay. So the more we look and the less we find, the worse it is for our own long-term survival, assuming that we are a typical kind of intelligence that exists throughout our galaxy. So the key point of this is that by looking out into space, looking out through our galaxy, searching for intelligent life, we're not just looking at our own past. We like to think about that as extragalactic astronomers, especially, that we look back in time, we look at deep Hubble Space Telescope images, we're seeing back in time, looking back billions of years. But by looking for these extraterrestrial intelligences, we are actually able to look at our future to see how long we might actually stay around. And this is a very interesting thing that we can now do as astronomers to answer some of these biggest questions that we have as humans. So I'll stop there. Thanks very much for your attention, and I'm happy to take any questions.
Thank you very much, Chris, for your talk. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in the YouTube channel and our speaker will answer them later.